So we are starting a new chapter, and it is the semiconductor, last chapter of the modern physics, right? And it is a very important chapter, semiconductor, right? At least two questions comes in the NEET, right, maximum, and in the JEE, the one question, definitely one or two question comes from this, right? Semiconductor, as it is very much clear from its name, it is a semiconductor, right? Semiconductor man, it is a half conductor and a half insulator. Sometime the material which is semiconductor work as a conductor, and sometime it may be act as an insulator. Are you getting or not? Can you tell me, Sanjay, what do you know about the semiconductor? You tell. Hello? Yes. What do you know about the semiconductor? What is the conductor? Conductor is like copper, Ag, Au, right? Copper, Ag, Au. These are the material conductor. In these type of the material, number of free electrons are available, and the electron density for the conductor which are used to conduct the electricity is approximately 10 is to about 28, right, per meter cube. So the electron density or electron number of electrons per meter cube are very high in this conductor. But the semiconductor like silicon and germanium, right? And also sometime there may be the semiconductor, compound semiconductor may be there, right? For example, these are the intrinsic semiconductor found in the nature. First of all, I would like to share, write the periodic table, the few elements of the periodic table, right? Li, B, B, C, N, O, F, Mag, Al, C, Pas, Ka, Sa, Ga, Gi, As, Si, Ba, Rab, Sar, In, San, Sab, Pi, I. But Tel, PB Lad, Bi Bismuth, polonium and statine. Polonium and statine, right? And Fra, right? Here helium, neon, argon, krypton, xenon, and radon, right? Kasbatal, Bi polonium and statine, right? So if you see, this is the first, right? This is the second, third, fourth, fifth, sixth, seventh, and the eighth group it is. Are you getting or not? Right. So if you you know what is the one atomic number, 2, 3, 4, 5, 6, 7, 8, 9, right? 9, 10, 11, 12, 13, 14, 15, like this. Are you getting or not? So if you consider the fourth group, this is 32, right? This silicon and germanium are the semiconductor. Are you getting? So although this is the carbon, carbon is sometime act as a semiconductor and sometime it act as a diamond, act as a insulator, right? The carbon may be of the two types of the graphite. It may be the carbon, I'm writing here, the carbon may be the graphite, right, and the diamond. So the graphite may act as a insulator and the diamond act as a graphite may act as a conductor and the diamond may act as a insulator, right? But for example, this is the aluminium, it is a conductor, all right, and this is silicon and germanium. These are the semiconductor material. Although the properties of these metals or the elements in the chemistry you have learned in a very well manner, but here we are only giving the focus on the silicon and the germanium. These are the eccentric elemental semiconductor, right? The types of the semiconductor, you can think the types of semiconductor. First, the elemental mean which are found in the form of the element only, elemental semiconductor, right? Elemental semiconductor, what are the silicon and germanium, that's it. Second is the compound semiconductor, right? Compound semiconductor mean in the physics lab, in the lab, chemistry lab, you can make the semiconductor by combining, for example, gallium arsenide. If you mix the gallium arsenide in the some ratio gallium arsenide, so this is the semiconductor, compound semiconductor. Indium phosphide, INP, this is also the semiconductor compound. And gallium phosphide, GAP, right? GAP, gallium phosphide, gallium arsenide, indium phosphide, and gallium phosphide, these are the semiconductor. The gallium arsenide is a very important compound semiconductor which is used to form the LED. Do you understand the LEDs? The light which gives the light, right? The small LEDs are made of gallium arsenide. Although the elemental semiconductor silicon and germanium we are going to discuss, right? The carbon may act as a semiconductor, right? It is semiconductor, or it may be conductor, or this is found in the two way. This is found in two form, and this is insulator. Are you getting or not? Right? If you consider the silicon, the 14th, can you write the electronic configuration of silicon? This is 1s2, 2s2, 2p6, 3s2, and 3p2. You will see in the semiconductor, this is in the third, right? Third period, and the fourth group, it is over there, and the last, in the last orbit, how many electrons are there? The 4 electrons are found. In the same way, if you consider the 32 germanium, 1s2, 2s2, 2p6, 3s2, 3p6, right? 1s2, 2s2, 2p6, 3s2, 3p6, 4d10. Can you tell me 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 4s2, 3d10, and 4p2. So if you make this in a correct way, 2p2, 3s2, 3p6, 3d10, 4s2, and 4p2. So if you consider the last orbit of the germanium, again there are 4 electrons are found in the last orbit. So if you consider whether silicon or germanium, in the last orbit there are 4 electrons are found in the germanium and the silicon, because these are in the fourth group. Are you getting or not? Right? Copy this. So this is the basic for the semiconductor, basic information for the semiconductor. In the fourth group, silicon and germanium are the elemental semiconductor. Although the semiconductor may be formed by combining gallium arsenide, gallium phosphide, indium phosphide, like that. So these are the compound semiconductor and the elemental semiconductor. Some other type of the semiconductor I'm writing here only, and this is the organic. These are called the organic semiconductor, right? And sometime the inorganic semiconductor is also there. Semiconductor, the inorganic semiconductor, they may ask, for example, anthracene. This is the compound semiconductor which is inorganic in nature, and its structure is like this, right? You may write this. This is the anthracene, right? like this, like this, right? This is the anthracene semiconductor. Did I make it correct? Yes, this is the anthracene. Is it correct or not? This is the structure of the anthracene. Right? It is a little bit theoretical, right? Yes, I think it will be like this. No, this is the anthracene. Copy this. So we can classify the semiconductor in the two bases. First, on the basis of the conductivity, right? You may write classification of semiconductor. First, on the basis of conductivity. Right. For example, we have the solid type of the solid. The solid may be classified in three ways. The three part: the conductor, semiconductor, and insulator. If we compare the conductivity, right, and we may write the resistivity, right. So the conductivity of the conductor is very high and the conductivity of insulator is very low. The conductivity of semiconductor is in between. It is less than the conductivity of the conductor and more than the insulator. If you give the value, and the conductivity of the conductor is very high, 10 to the power 8 to 10 to the power 2 Simon per meter is the conductivity. Are you getting? While the conductivity of the insulator is very high, very less, it is less than, the conductivity is sigma is less than 10 to the power minus 6, right, Simon per meter. Are you getting? While the conductivity of the semiconductor is in between this, it is greater than 10 to the power 2 to 10 to the power minus 5 Simon per meter. You understand this thing or not? While the resistivity of conductor is very less, but the insulator it is very high. The conductivity is very high. It is more than 10 to the power 6, right? More than, this is the resistivity is more than 10 to the power 6 ohm meter. Ohm meter is the unit of the resistivity. It is very high, but the conductivity is less, very less, 10 to the power minus 8 to 10 to the power minus 2 ohm meter, and the resistivity is in between 10 to the power minus 5 to 10 to the power minus 2 ohm meter. So for the semiconductor, the conductivity is less than conductor and more than the insulator, while the resistivity of the semiconductor is less than resistivity is more than the resistivity of conductor and less than of the insulator, right. The insulator are like wood, plastic, right. These are the example. The semiconductor is silicon, germanium. The conductor is aluminium, copper, silver, like this. So these are the solids, and we can classify these solids in terms of their conductivity and the resistivity. Is it clear? Copy this. So now this is the classification. It was the classification on the basis of the conductivity. Now in other way, we can also classify it on the base the semiconductor, the solids, in the form of the energy bands, right. The classification, second classification on the basis of energy bands, on the basis of the energy band. Listen one thing. If you consider in the atomic structure, you have seen, if you consider an atom, right, in the atom the electrons are occupied in the different discrete energy levels, right. For the atoms, the energy for the atom, any atoms, the energy level of the electrons are discrete. Suppose this is the 1, 2, 3, 4. For the hydrogen atom, right, you may consider this the n is equal to 1, n is equal to 2, n is equal to 3, n is equal to 4. Right. If you consider n single element or the single atom, then the energy level are discrete. For single atom, we have considered in atomic structure, right, the discrete energy level, energy level levels are there. Are you getting or not? Do you understand or not? But when the solid is formed, solid is formed. So what happened? When the solid is formed by joining the atoms, right? Number of atoms come close to each other. Solid is formed. Number of atoms are come close to each other. Come close to each other to form the solid, to form it. So due to interaction between different energy level, right, different energy level. Suppose we have, this is the single atom and the energy levels are different. Whatever the value of the energy in electron volt, I am not considering, only these are the discrete energy level. Suppose the silicon like this is the silicon, right? So many number of atoms are come close to each other to form the solid. So when their discrete energy levels, right, are like this, are you getting or not? These are the discrete energy levels of every individual atoms, right, like this. So these energy levels are interacted. Because of the interaction between the atoms, these energy levels are slightly shifted. Are you getting or not? For example, if you consider a piece of the solid, millions of billions of the atoms come close to each other and they form a very structure to form the solid, right? So what happened? For example, it's n1 level, it is the first level, it is the first level. So when they come close to each other, their energy level slightly deviated from their original value. For example, if this is the representation of the energy level for the single atom. For many atoms, what happens? For n, but n is equal to 1. So the energy levels near the n is equal to 1. So this is the energy level n is equal to 1, right? So if suppose there are 9 atoms, so all the 9 atoms have the 9 orbits and the 9 electrons are there. 9 electrons, 1, 2, 3, 4, 5, 6, 9. So 9 electrons are there, but now suppose the energy is 13.6 electron volt for the hydrogen. So every atom for the every energy level is not exactly 13.6. Because of interaction, the energy level become 13.60001 like this. Other energy level become 13.60002 like this. So the discrete energy levels are there, but they are very close to each other for the first energy level, right? And in the same way, for the second energy level, like this. So these energy level come close to each other, right? When the solid is formed with the help of the elements. In the same way, these are the energy levels. Are you getting or not? Like this, right? N is equal to 3. So these discrete energy levels of the solids form the band, and these bands are called the energy bands. Do you understand what is the energy band? Sanjay, tell me what is the energy band? Hmm. Hmm. Like that. Yes. In the same way, in the n barabar 2, although it is 3.4 electron volt for the hydrogen, but if we consider the solid, right, some other solid you may consider, so the energy levels are slightly different from the exact 3.0. So although all the electrons have the discrete energy level, right, but they are very close to each other, and these are form the energy band, right? These are called the energy band. Between different to form due to the interaction between different energy level, due to number of atom come close to each other, and due to interaction between different energy level, right, they form energy band. They form energy bands. They form energy bands. They form energy band in which every electron occupy discrete energy level. Discrete energy level. Discrete energy level. Is it clear or not? Right. For example, listen one thing. Although, how many energy levels are there? Can you tell me? How many energy levels are there? Sanjay, for any atom, how many energy levels are there? Infinite. Right. If you consider the silicon, suppose 14, right? 14. 1s2, 2s2, 2p6, 3s2, 3p2. Right. This is the first, second, and third. So I'm writing this for silicon only. You may write for any atom in the same way. This is the first, second, and third. So, in general, if you consider the silicon, the electrons occupy in these orbits. In this orbit, although the orbits are n is equal to 5, 6, 7, 8, 9, 10, 11. So, if you consider 1, 2, 3, so these are the energy bands where the electron resides in normal temperature, right? And these electrons are called valence band. Valence band. What is the valence band? In which the electrons occupy the different energy levels. Are you getting or not? Different energy level at normal temperature. Valence bands are the energy levels, right, where electrons electrons stay at normal temperature for semiconductor. When these electron gets the energy from the outside, suppose for the silicon, this is the silicon, right? Silicon atom. So electron may be there, right? Like this. The 4 electrons are in the third energy level, like this, right? So when the energy they get from the outside, the electron jump to the higher energy level, and these are called the valence band, and above this, these bands are called the conduction band. This is called conduction band. Do you understand? So this is the, listen one more thing. These electron does not leave their orbits. Only the electron present just previous to the conduction band. These electron may jump only to the higher energy level. These electron does not jump. So these electrons, this is especially, this is called the valence band, and this is called the conduction band, right? So in general, at lower temperature, the electron remains in the valence band. When they get the energy, they move to the higher energy level, and these band, right, above the valence band are called the conduction band. What is the use of the valence band and the conduction band? When the electron moves to the conduction band, so the conductivity of the material or the conductivity of the semiconductor is increased. Do you understand or not? What is the difference between the valence band and the conduction band? The valence band are the discrete group of energy levels, right, in which the electron remains in the normal temperature. But if these atoms or the electron get energy from the outside, it move to the higher energy level where this electron is free from the interactive effect of the nucleus, and it is free to move inside the space between the atoms, and it is available for the conductivity. So that is why it is called the conduction band. Are you getting or not? Right, listen one thing. So this is the conduction band and the valence band. The energy gap between this conduction band and the valence band is, right, the energy difference is called the energy gap. This is what? The energy gap. Energy gap is delta V, right? Delta V. Energy gap between the conduction band and the valence band. It is the energy gap. Please copy this. So this is the energy bands, right? The valence band and the conduction band. What is the band? Band are the group of discrete energy level, right? What is the band? Group of the discrete energy level. Normally the electron remains here, right? When atom get the energy, atoms get the energy from outside, right? Electrons in the valence band, jumps to the conduction band, right? Conduction band, where in conduction, where they are available for conductivity. They are available for conductivity, right? They are available for the conduction of the current of the conductivity, right? Therefore, listen one thing. At normal temperature, they are available for the conductivity, right? So at normal temperature, semiconductor acts as an insulator, right? As an insulator. And at high temperature, same semiconductor act as a conductor. Are you getting or not? Why it acts as a conductor? Because the electron jumps from the valence band to the conduction band, right? First copy this, I will explain further. So how to differentiate between the solids, right? How to classify the solid on the basis of the band theory, right? For the solid, for insulated, I'm discussing the classification of solid on the basis of energy band theory, right? For insulator, like plastic or wood, right? Plastic. So if you consider, this is the conduction band and this is the valence band. So this is the conduction band and this is the valence band. Are you getting or not? For the insulator band. So these are the different energy levels are available. In the conduction band. So listen one thing. This is the energy gap. This is the EG. Is the energy gap. Energy gap. The energy gap is greater than 3 electron volt. Are you getting or not? Suppose if you consider this the plastic, and the electrons are available in the valence band, right, like this. But when this pen or the material, this material get the heat or the energy from the outside, these electrons are not able to cross this energy gap. They can never reach to the conduction band. Are you getting or not? Therefore electrons are not available in the conduction band, right? And the valence band is full and the conduction band is empty, right, at every temperature, right? So no electron is available for conductivity, right? Why it is so? Because energy gap is, since energy gap is very high. Do you understand? And electrons are not able to cross this gap. So no electron is available for conductivity in conduction band, right? This is the reason. So why this is called the insulator, right? Copy this. In this case, the valence band is full and the conduction band is empty, right? Therefore the insulator are not conducting, right? Why? In case of metals, second, in case of metals, what is the thing in case of metal? Like aluminium, copper, right? If you consider this the conduction band, and the valence band, conduction band and valence band overlap each other, right? Conduction band and the valence band overlap each other. This is the conduction band and the valence band. So what are the electrons are available in the valence band? They are automatically available for the conductivity in the conduction band. For the metals, conduction band and valence band overlap each other, right? And therefore all the electrons in valence band are available in conduction band for conductivity always. Do you understand or not? Right? If you consider a metal piece, if you consider this the metal, suppose a metal piece, so the electrons in the valence band already automatically present in the conduction band. So therefore the number of free electrons are available in the conduction band, therefore it has the more conductivity, right? Copy this. While if you consider the semiconductor, for semiconductor, what is the difference on the basis of the energy band? If this is the conduction band and this is the valence band, so the energy gap is less than 3 electron volt, right? So it is very small as compared to this. Do you understand or not? So what is the property of this semiconductor? At lower temperature the electron occupy the valence band. When at high temperature, when the energy is given to this material, so these electrons reach to the conduction band, and therefore they are now available for the conductivity in the conduction band. Therefore these are called the semiconductor. Why it is semiconductor? At low temperature the electron occupy the valence band, at high temperature the electron reach to the conduction band for the conductivity. Do you understand or not? You tell. Right, I'm writing at low temperature, electrons occupy the valence band, and at high temperature electron jump to conduction band. Therefore they show the conductivity. more conductivity, more conductivity, right? That is why these are called insulator. Copy this. Can you explain what I taught you for the how to differentiate the insulator metal and the semiconductor in on the with the help of the energy bands? For the metals, the energy bands overlap. Therefore, all the electrons in the valence band automatically available in the conduction band. The energy gap for the insulator is very high. Even if you provide the energy, if you raise the temperature, no electron is reached to the conduction band. Therefore, they are insulator. But for the semiconductor, energy gap is less than 3 electron volt. I will give the energy uh, gap for every semiconductor, right? So you will see it get the energy even at the room temperature. Energy mean not the heat, rather at the room temperature. At high temperature, the room temperature is also consider, right? Temperature is the 27 degrees centigrade, right? It is 300 Kelvin is sufficient energy, high temperature, sufficient high temperature for the conductivity. At the room temperature also, the electron from the valence band, they reach to the conduction band for the semiconductor like silicon and germanium. So at room temperature, this silicon and germanium are conductor. Do you understand or not? Right? At room temperature, silicon and germanium are conductor. But if you reduce the temperature, make them cold, so they does not show the conductivity. Do you understand or not? So if you consider the very low temperature where the in the like Kashmir, right, or some other place, right, on the poles, right? So it is not necessary that all the devices which are working here in this atmospheric condition, the same device will work over there. It is not like that. So because the property of the material, so therefore the device for the different weather condition at low temperature, at minus temperature, the device are made of different elements, right? That is the thing. Do you understand or not, Sanjay? Right. For the different, now we are not going to discuss the insulator, we are not going to discuss the semi metals, we are discussing the semiconductor, right? So for different semiconductor, the energy gap is different. For example, right, for silicon, if you consider the silicon, germanium, the gallium arsenide, and the gallium phosphide, the indium phosphide, right, indium phosphide, the energy gap at room temperature is 1.1 electron volt. This is the energy gap, right, at room temperature, right? And this is 0.72 electron volt, the 1.4 electron volt, this is 2.2 electron volt, this is 1.3 electron volt. You don't have to remember all these. At least germanium and silicon energy gap you have to remember. What is the energy gap for the silicon and the germanium? This is the energy gap. This is the conduction band, this is the valence band, right? It is more for the germanium, the energy gap, this is the energy gap, is what, 1.1 electron volt. The energy gap is equal to 0.72 electron volt for the conduction band and the valence band. Is it clear or not, Sanjay? Listen one thing. Although the energy gap at room temperature is given, the important note for the energy gap. The energy gap depends upon the temperature, right? And energy gap as a temperature for silicon, I'm considering, it is 1.21 minus 3.6 into 10 to the power minus 4 into T temperature. And for the germanium, the energy gap as a function of temperature is 0.78 minus 2.23 into 10 to the power minus 4 into T. These are the energy gap in electron volt. At room temperature, right, at T is equal to 300 Kelvin, right, this energy gap become, when you will calculate, it become 1.1 electron volt. This is the room temperature energy gap, right? And for this, at T is equal to 300 Kelvin, the energy gap become 0.72 electron volt. Is it clear or not, Sanjay? What is the conclusion? The conclusion is that at the temperature is increased, this energy gap is also reduced. As temperature T increases, the energy gap is also reduces. Do you understand this? Copy this. So this is the basic theory for the semiconductor. The different types of the semiconductor have the different energy gap, and for the different purpose we use the different semiconductor in the different applications, right? So okay, so this is the basic of the semiconductor. Now the semiconductor, we can start with the initially the semiconductor found in the nature in the pure state is called the intrinsic semiconductor. Are you getting? So first I will discuss the intrinsic semiconductor. Intrinsic semiconductor. Intrinsic semiconductor. What is the intrinsic semiconductor? The semiconductor in pure state. Semiconductor in pure state without impurity is called the intrinsic semiconductor, right? For example, the silicon and the germanium, right? Silicon and the germanium. So if you consider the silicon and the germanium, 1s2, 2s2, 2p6, 3s2, 3p2, right? For the germanium, this is the 4s2 and 3p2. 4s2, 4p2 will come in the last. Understood? So if you consider the silicon. So how many electrons are there in the outermost shell? You tell. In the outermost shell, tell me. This is the silicon. 4 electrons are there. 4 electrons in the every silicon atom city, right? So they combine like this. For the stability, they form the covalent bond with nearby silicon atom like this. Do you understand or not? So this type of the semiconductor found in the pure state without impurity, this is called the intrinsic semiconductor. Are you getting or not? Copy this. So these are the semiconductors. Suppose this is the silicon block, right? And when this silicon block is connected to the battery, so how does the current flows with the help of this semiconductor? I will tell you, right? So I will explain the conduction process. Conduction process in intrinsic in semiconductor. Right? How does the current flows in the semiconductor? Listen, one more thing. When the temperature of this when temperature is increased, so what happens when the temperature is increased? When the temperature is increased, this is the covalent bond, right? This one covalent bond is break. And therefore when the one covalent bond is break, this covalent bond is formed by the 2 electrons like this, and when one bond is break, the electron is released, and therefore a vacancy is created over here. This is the free electron. As when the temperature is increased, covalent bond breaks, and an electron is released. For conductivity, for conduction. Electron is released for conduction. This is called the free electron is released for conduction, and vacancy is produced, and a vacancy is produced. This vacancy is equivalent to the positive charge, and this is called hole. This vacancy is called hole, or sometime it is called as the Keter. It is equivalent to positive charge. It is equivalent to positive charge. Do you understand or not? So if you consider the semiconductor, and when the temperature is released, so when a covalent bond, sometime this covalent bond also maybe break. Are you getting or not? So inside the semiconductor, the free electrons are available like this, and intrinsic semiconductor, if number of free electrons are 2, so the number of holes will also be 2. If these are 3, these are 3. So in the semiconductor, what are the charge carrier available for the conduction process? There are two types of the charge carrier are present in the semiconductor. One is hole and another is electron. Are you getting or not? You tell. Right? So therefore, I am writing here, therefore, in semiconductor, in semiconductor, conduction process is due to an electron as well as due to hole. Do you understand or not? Copy this. On the basis of the band theory, right? This is the explanation of the conduction process in semiconductor on the basis of the band theory. The one covalent band is broken, and electron is released and hole is released. Listen, in terms of the conduction band and the valence band, are you getting? When the temperature is increased or at sufficient temperature, at room temperature, when the electron from the valence band jump to the conduction band, so electrons comes over here, and hole or the vacancy is produced in the valence band. So this is the hole and this is the electron. Are you getting or not? So this is the explanation how does electron and the holes are produced, and when this material is applied across a potential difference is applied across this material, so what will happen? You tell. What will happen? This is equivalent to positive charge. Electron start moving in this way and the hole start moving in this way. This electron start moving in this way and the hole start moving in this way. This electron start moving in this way, electron start moving in this way, and this hole start moving in this way, So there are two type of the charge carrier in the semiconductor, right? The electron and hole, and the current is due to what? The current, listen one more thing. In this case, the number of hole or the number of charge carrier of the electron and the number of charge carrier of the holes are equal, and this is called the Ni, intrinsic semiconductor concentration. Intrinsic carrier concentration, right? So Ne is equal to Nh, what? Number of electrons per unit volume is equal to number of holes per unit volume. Both are same, and it is called intrinsic carrier concentration, Ni. Do you understand or not? Right. And the current in this case is the current due to the electron plus current due to the hole. Is it clear or not? due to electron due to hole, right? Copy this. Sanjay, if you consider the conductor, what is the formula for the current in the conductor? If you remember, the current is equal to NEAVD. Are you getting or not? Did you remember or not? And VD is equal to what? Say mu into E. NEA mu into E. I upon A is equal to NE mu into E. Is it clear, Sanjay? And this is called the density is equal to sigma into E. The carrier, the current density it is. Is it clear or not? You tell. And the conductivity is what? Mu into E. So the current, right? Sigma. What is the sigma value? Sigma is NE mu, right? So if you consider the current density in this case is equal to current density due to electron and due to hole. What is the current density? Current density is sigma into E. Sigma of electron plus sigma of hole into electric field. What is sigma? Sigma is the conductivity of the electrons and sigma H is the conductivity of the hole, which is equal to, what is the sigma value? Say NE mu, number of electron and the electronic charge, and mu is the mobility of the electron, plus what is the sigma of hole? N, number of holes, plus electronic charge plus mobility of hole multiplied by electric field. Is it clear or not? So the current density in semiconductor, because of the electron current density and hole current density, if you take electronic charge common, so this is Ne mu E plus NH mu H into E. Do you understand or not? You tell. Although for the intrinsic semiconductor, the Ne and NH both are equal, I am writing here, but for intrinsic semiconductor, Ne and NH is equal to Ni, right? You can put the value, you can get the value of J is equal to E, right? Ni into mu E plus mu H into E. So this is the current density in the semiconductor in terms of Ni, intrinsic carrier concentration, mobility of electron, mobility of hole, and the electric field applied by this potential difference. Copy this. So do you understand the semiconductor conduction process in the semiconductor? Can you explain once again, please? Can you repeat this? Right. Right. Carrier concentration. It is equal to the intrinsic carrier concentration when the semiconductor in pure state, right? The electron and hole concentration are equal, and this is called the intrinsic carrier concentration, right? And both contribute to the total electric current, and this electron is not emitted, rather a covalent bond is broken and an electron is released, right? And equivalent positive vacancy is produced in the form of the hole. Do you understand or not? So when the potential difference is applied, the electron and holes both are moved inside the semiconductor. Is it clear or not? Yes. For example, For example, in an intrinsic semiconductor, number of free electron, number of conduction electron is 2.5 into 10 की power 13 per centimeter cube. Right. Find total number of charge carrier in semiconductor of size 1 centimeter into 1 centimeter into 1 centimeter. Right. So this is the semiconductor, 1 centimeter, 1 centimeter and 1 centimeter. Right. And the total number of conduction electron in this case, total number of electrons, conduction electron per centimeter cube is given, right? Per centimeter cube. And this is the total volume. You have to find the total number of charge carrier. This is the very simple and the important question. Copy this. So how to find the number of charge carrier? What is the volume of this semiconductor you tell? 1 centimeter cube. Are you getting? This is the 1 centimeter cube. For 1 centimeter, Sanjay, make it correct. It is 1 millimeter, sorry. 1 centimeter, and it is 1 millimeter. So the volume is what? 1 into 1 into 0.1 centimeter. It is 0.1 centimeter cube. Are you getting or not? So these are the electrons per centimeter cube. So can you tell me total number of electrons? Total number of electrons. How to find the total number of electrons, Sanjay? Yes, into the volume. This is the electron density. What is it? Electron density, right? Or the free electron charge carrier density. This is multiply 10 की power 13. It is 0.1. It is 2.5 into 10 की power 12. Electrons are present. Are you getting or not? Copy this. So these are the okay. So these are the number of electrons. So how many electrons are there? Same number of holes will be there. So total number of holes. You tell. What is the total number of holes? The 2 times of 2.5 into 10 to the power 12. Right? You can copy this. You complete this. So this is 5 into 10 to the power 12. The total number of holes are this, only this, and the total number of charge carrier, you can multiply 2 into 2.5 into 10 to the power 12. It is 5 into 10 to the power 12. Is it fine? Right. Very good. Suppose, listen one thing. If you want to find the conductivity, for example, find its conductivity. It's find the conductivity of semiconductor. If, listen one thing, mobility of electron and the mobility of hole are given in the question. This is 3800. This is 1800. Mobility of electron and mobility of holes are given. All right. And the intrinsic carrier concentration. What is the intrinsic carrier concentration? Is same as the carrier concentration of electron and holes. Are you getting? So it is 2.5 into 10 to the power 13 per centimeter cube. And the unit of the mobility of the electron is 3800 centimeter square per volt second, centimeter square per volt second. These are the unit of the mobility of this is the unit of the mobility of electron and mobility of hole. The intrinsic carrier concentration is given 2.5 into 10 to the power 13. Is it clear or not? You tell. So listen one thing. What is the conductivity formula for the semiconductor? The semiconductor conductivity is the sum of the conductivity due to the hole and the electron and due to the hole. Do you understand? Sigma is what? Ne mu. So this is electron carrier concentration, E into mu of electron plus hole E into mobility of hole. Is it clear or not? Sanjay, this is Ne into mu E plus NH into mu H into E. So this is the conductivity of semiconductor, conductivity of semiconductor. So Ne, what is the Ne? For the intrinsic semiconductor, Ne is equal to NH is equal to Ni. What is Ni? It is called the intrinsic carrier concentration. Intrinsic carrier concentration. Right. It is intrinsic carrier concentration. It is given. So it is 2.5 into 10 to the power 13. What is the mobility of electron? It is 3800. The whole concentration is same. I will write 2.5 into 10 to the power 13, and the mu h is 1800, and multiply by 1.6 into 10 to the power minus 19. When you will calculate, right, you will get 0.00, right, 0.0224 Simon per centimeter. So this is the conductivity. And if you find the resistivity, the reciprocal of conductivity 0.0224, which is equal to 44.6 ohm centimeter. Do you understand or not? Should I explain this once again? Listen, one more thing. If you understand, what is the purpose of doing all this calculation? The purpose is that this is the very important question. First of all, they will ask the total number of charge carrier in the intrinsic semiconductor. If this is the total volume, multiply by volume, you will get the charge carrier. The electrons and the holes are the same, and when you multiply by 2, because it is 2 times the electron plus hole. But if you consider the conductivity, this is the practical data which is given in the question. Also, this is the intrinsic carrier concentration we have given in the question, or this is the practical data. If you try to find the conductivity of the semiconductor, the conductivity practically comes out to this of the semiconductor. Even the electrons and holes both are moving in the semiconductor. Is it clear or not? But the conductivity of the semiconductor is very less. I am writing here the important note. What is that? It is clear that conductivity of semiconductor is very less, very less. So therefore this semiconductor is useless. Therefore this type of intrinsic semiconductor is useless in terms of conductivity.